Alright, this is the virtual lecture for October 27th, and in this lecture introduction you will go to your integrity recordings and go through the simple harmonic motion recording here that you see on the screen, and then following that we'll have our set of problems here, okay, involving simple harmonic motion, which will involve two systems, the mass on a spring and a simple pendulum. The first problem, spring mass system. Here we have a mass on a spring oscillating with a period of 0.85 seconds and an amplitude of 11 centimeters. You'll have to look in Chapter 9 to see how those terms apply. Period, amplitude. Also at time t equals 0 seconds, we are told that the mass is located at 4 centimeters, so that's its position x at t equals 0. We're told it's moving left, alright, so it's at minus x, negative velocity. What are its position and direction at a time 2.2 seconds? Okay, so you would take a look at, for example, if we went into Chapter 9 here, Chapter 9, Vibrations in Simple Harmonic Motion, and read down through here, and we come to simple harmonic motion. Here's a picture of our mass and spring system and our pendulum, and we scroll on down and in particular focus on the mass and spring system. We can derive a solution for the equation of motion that tells us what x is related to right here. Okay, all right. Now the second problem also involves a spring and mass system, but it focuses on the principle of conservation of energy applied to this system. Here we have a spring that is pulled out 18 centimeters and a mass on the end of that spring and released, and it oscillates back and forth, and we're told that the period of the oscillation is 0.85. okay, we've got that, and we want to know at what point x is the speed 1.1 meters per second. So we've got our mass, we've got our amplitude, we've got our time, and we've got our velocity. Similarly, if we go back to the book, we can look in the area where we discuss energy, kinetic, potential, and total energy, find that the conservation of energy principle between the total energy of the mass at its maximum displacement of its amplitude A, it relates to the kinetic and potential energy stored in the spring. We get this expression that we see down here, which we can use. Okay? All right. The next problem is the third problem, and the last problem involves a pendulum, which is also a simple harmonic system, because the pendulum bob continues back and forth to cover the same distance, same path that it had before, and it's a restoring force, which is what a spring system is. So here we have a mass 250 grams on a 25 centimeter string. We're told that it has a speed as it passes down through the bottom of the arc. Okay, so that's the point where it has its maximum speed. It's all kinetic energy at that point. There's no potential energy remaining, and we would like to know what is the angle through which the pendulum swung from its maximum up here down in angle down to 0 angle, where it has its maximum kinetic energy. We can flip back to our book and take a look at some information about the simple pendulum. There's a couple example problems as well. So that should be sufficient to get you going on that, and then submit those three problems for October 27th into Ferris Connect. The title of that assignment is Virtual Lecture for October 27th. Thank you.